Hi, today I'll be going to the solutions to the first practice midterm for PHYS 457. Now the question 4. Now the first question 4 asks, for this, two effectively infinite sheets of current contain a space of width W. For this part, the left sheet contains a constant surface current K y hat, and the right sheet contains a constant surface current of negative K y hat. What is the energy density, energy per unit volume, from the magnetic field in the empty space? So before we do anything, the first thing we want to figure out is what is the magnetic field. Now the magnetic field, not the magnetic field, but the direction of the magnetic field first. So how do we do that? Well, just apply right-hand rule. So let's look at the contribution from this plate. It's going out of the current, the surface current is going out of the page, and so this implies a B field, and so from the contribution from this side is going in the positive z hat direction, and then similarly this is going into the page right here, so the contribution is also going in the positive z hat direction. So from the summing the contributions, you just get a B field going in the positive z hat direction. Now the next step that we need to figure out is we need to figure out what the B field actually is. So how would you go about that? Well, the most straightforward application would be to apply one of Maxwell's equations. In particular, this one. Mu naught I closed. So how would you go about doing? But we need to do this, we need to draw some sort of Amperian loop to figure out what this term will be. Now, if we draw our Amperian loop just in some arbitrary point, like I'll just draw it here. And from here it doesn't and from here we could see that, oh hey, this L is collinear with B, and then we also, and all the other components kind of cancel because so the width of this loop doesn't really matter because the flux entering from the bottom is equal and opposite to the flux from the top, and so you end up with a BL term, which is equal to mu naught I enclosed. And what is I enclosed in this case? Well, I enclosed should just be what the surface current K times mu naught. So it should be, the surface current K times L. So you end up with KL. And so the L's cancel right here. And then you end up with a B field of mu naught K Z hat. Actually, I'm going to write this over here because mu naught K Z. Okay, Z. Okay, Z hat. So this is your B field. And from this, you also, and to determine the work per unit, the energy per unit volume, you simply compute the work integral, which in this case would just be 1/2 mu naught times the B. That's a really poor pen. I'm going to switch over to something else. B squared d tau. Now this just simplifies down to 1/2 be mu naught squared k squared, which is then equal, and then times some volume term, which I forgot right here, which then leads to a total work done by work of mu naught k squared over 2 times the volume, and so the energy density U is equal to W over V, which is then equal to mu naught k squared over 2. And with that, that is the solution to this problem. Hi, today I'm going to be going through the solutions to practice midterm 1 for PHYS 457 part B of question 4. So we already know, so what does the question read? Well, it reads, for this part, the left sheet contains a surface current that is linearly increasing in time, kty hat. So that's this part right here. And the right sheet contains a surface current that is linearly decreasing in time, negative kty hat. Note that this is the same that k is the same constant in both of these expressions. A circular loop, connecting loop of diameter w is placed in between the two sheets, as shown in this figure. The loop has a resistance R. What current flows in the loop? Okay, so this as in the previous part of this question, part A, we have the B field going in the positive z hat direction. All that's really changing is that we have a linearly increasing and a linearly decreasing with time. But the directionality of the magnetic field is still the same. So, before we proceed, let's just quickly derive what the B field is. Now, the B field in this case is roughly the same thing as before, and it's just B dot dl is equal to mu naught I enclosed. So, and if you draw some sort of Amperian loop, like loop anywhere, you would see that the only real component that survives is BL, and from this bit, and then here you have a mu naught, and then the only thing and then just because this is a surface current, you have it's multiplied by k, so you have an LK, and then you have a T. And so these cancel, and then you're left with a B hat that is mu naught KT in the Z hat direction, which is very similar to what we got previously. The only real difference is that now you just have this time dependency T. So with that in mind, we can actually now calculate what theta of m is. So using this result, we can say that theta of m, or the flux, is equal to B dot dA. And so the area of this loop is just what? Pi. And so the flux we were concerned with is the flux through this loop. And so it's just pi r squared, but in this case our r is just w over 2. So then we are left with a mu naught kt w over 2 squared times pi. And from this, we can apply Faraday's law to obtain an expression for the EMF in the loop, from which we will then use to find what the current is. For now, let's just find the EMF. So we know what phi m is. So just take a derivative and you just end up with this lovely little expression right here. F u naught k pi w over 2 squared. And then this is, and so using just Ohm's law, we can figure out that this is, the EMF is I is equal to I times R. So from this, we can just rearrange. So this implies that I is equal to epsilon, the EMF over R. And so from this, we can infer, we then find that the current in this loop is negative mu naught k pi w squared over 4 times R. And with that, that is the solution to this question.